Hello, my name is Andreas Argubi-Wollesen, and I'd like to welcome you to this presentation about the analysis of repetitive movements. Especially kinematic and EMG analysis will be part of this presentation, and in order to do that, I will show you some parts of a research study on an occupational exoskeleton. So who am I exactly showing you this presentation? I'm a sports scientist based in Hamburg, Germany. Nowadays, I'm the head of Biomechanics in the research department of the XOIQ in Hamburg and Germany. My base is in biomechanic analysis, and I conducted research in the former years at the University of Hamburg and the University of the Federal Armed Forces, also based in Hamburg. So my expertise is especially the biomechanical evaluation of workplace scenarios in the last couple of years, especially when it comes to exoskeletons and ergonomical workplace analysis in general. So the XOIQ that I'm working at right now is based also in Hamburg and has been founded in 2017. It is based on the Smart Systems project that I've been working before at the Federal Armed Forces University, and our goal is to develop intelligently constructed support systems that could enhance humans' lives at the workplace to reduce physical load and to reduce ergonomical problems that might occur while doing manual labor. In order to give you an overview about the problems that occur with the exoskeletons and why we conduct the study, especially that I will show you, I have to go back to the definition of what an exoskeleton really is. So it is an electromechanical system that is worn by a user. That's a distinctive characteristic. It transfers mechanical energy onto the human body via the interfaces, and it could be distinguished between different body areas which the exoskeleton will support. Because if you look at the field of occupational exoskeletons that are available on the market right now, you will see that most of them will support a specific body area, like the shoulder or the back or the knees, but not the whole body in itself or overall. So exoskeletons that will support every single joint in the human body, these are not realistic exoskeletons that you will find in occupational use nowadays. This is still part of science fiction because exoskeletons that would do that are nowadays with today's technology would be too bulky and too heavy to use in the occupational world. So also we can distinguish exoskeletons on the market right now based on its characteristic. So what kind of materials are being used to apply the force to the users, and we have rigid elements. For example, on the left-hand side you see an example for an exoskeleton for shoulder support. There are rigid elements, and on the right-hand side you see an example of a back support exoskeleton, and these will use mostly soft structures insofar that exoskeletons could only use textile components and are completely get rid of rigid elements, and these are a special category, and we call this category exosuits, for example. Also, another distinguishing factor is the actuation itself of an exoskeleton. Could be a passive one. So passive means it uses pure mechanical system like springs, and an active exoskeleton will use electric motors or pneumatic systems, which are in the end electromechanical systems, which means I can alter the force that is applied on the human body while using the system. So when we look at the goal of an exoskeleton, it is to reduce the overload. We want to keep a healthy amount of load onto the human body, but as the peak of the load that we apply during the work conditions on the human are problematic or could be problematic and could lead to musculoskeletal problems, we want to reduce the total amount to a healthy amount of load that is applied on the human body while working. Looking what kind of analysis has been conducted in the past for shoulder support, especially also for exoskeleton, especially for shoulder support, for example, we see that mostly muscle activity has been looked at. So we see in most cases the analysis by conducting EMG amplitudes, and we have in most cases a reduction in maximum or average muscle activities while working with an exoskeleton. And overall you can say that most of the exoskeletons that are created for shoulder support will show an overall reduction in muscle activity. So if you look at what is not known, where's the knowledge gap, it is that as you look at the average or the maximum or minimum activity of muscles being used while using an exoskeleton, we do not know what the real muscle activity is taking, or what kind of muscle activity is taking place outside of this distinctive characteristic points in time. So what's really happening during the whole movement phases, or what kind of joint angles are represented when the exoskeleton is helping the most or the least, we do not really know that. So there's a knowledge gap that we were interested in. Looking at the kinematics, so the motion and the trajectories, we see a lot less studies being conducted about that, and also there's in most cases just a pure detection of maximum averages when it comes to the kinematics and the joint angles. And we see that for example with the exoskeletons being available up until that point of that study that I will show you right now, we see that sometimes we see a significant reduction, for example in shoulder flexion and abduction. So also we do not know what kind of changes occur in motion trajectories overall. So during the whole motion, in most cases, the studies that have been conducted, they're looking at distinctive points, and so the altered muscle, the altered joint angles, for example, are still unknown. The exoskeleton that we wanted to do research on, it was a self-developed one. It was one of the first active exoskeletons. It was an exoskeleton using pneumatics to create force. And as you can see here in that picture, it was a backpack-like carrier structure. Force has been supplied through the interfaces below the upper arms, and the support structure braced itself against the hip belt. So comparable to a traffic backpack that you have, where you can carry a lot of load in comparison to a normal backpack. It is able there because the load is transferred onto the hip, and as well the same concept is being applied with this kind of exoskeleton. So the force, the load of the tools you're wearing, and the force itself, everything is braced against the hip, and the load is transferred from the weaker body area, the shoulders, onto the stronger body area, the hip itself. So just in part research question that we had in this study, and in the part of the study that I want to show you when it comes to the repetitive motions, was do the use of the exoskeleton alter their working habits, such as are the kinematics of the upper limbs altered in any way, and do we see a reduction in muscle activity for the shoulder, because as the exoskeleton was conducted to reduce muscle activity while working with power tools, then of course we were interested in the possible reduction of the muscle activity. Of course, being a researcher, I'd like to show you the test population of our research project. I don't want to go into much details because it's not of any specific interest for this presentation, but what I want to stress is that we had a calculation of the sample size, which is really important when it comes down to the statistics, because you really need a proper sample size for the kind of statistics you will do in order to have a powerful statistical outcome. If you use not enough test subjects, then the power of your statistics will be weakened, and therefore we strongly suggest using a priori sample size calculation, for example with G-power. So we used male participants in this study, and you can see there's the anthropometric data of the test population, but this is not of too much interest in detail right now. I want to show you the analyzed work sequence that I will stress in this particular presentation. It was just a part of the study, but you see here work sequence riveting at the ceiling at the lab, and we have the work sequence riveting with and without exoskeleton. And as you can see here, the motion is repeated over and over again. This is based on work and analysis we did at several different places where we have this highly repetitive motion conducted all over the place and all day long, so puts a lot of stress on the shoulders, and this is why we showed this work sequence. And as you can see here, like with walking or cycling, we have a repetitive motion, and due to the fact that it is repetitive, we have specific statistical analysis we can do, which I will go on to later. So first of all, we have to sequence the whole movement structure into phases. So in this case, we have an upward motion until the riveting pistol reaches the top, and we have a downward motion in which the pistol is loaded again with a new rivet. To do the analysis, we had certain measurements and instruments being used. We used 3D kinematics, so a Vicon system has been used, 8 cameras, and we use a specifically designed upper limb model because we were very interested in the motion that occurs at the upper limb especially. So, and we reduced that to the extent that we were looking specifically in this presentation right now, the flexion and extension of the arm, so shoulder flexion, and as well as the abduction and adduction motion. To gather information about the muscle activity, we used electromyography, we used standardized protocols, we used Xenium gait lights, and in order to make sure that we don't have any motion artifacts, we use specifically 3D printed, based on 3D scans, anthropometrically formed cover plates, so that the exoskeleton will not alter the outcome of the EMG data. So the variables that we were looking at were the activity of the upper shoulder girdle, muscular trapezius, deltoideus anterior, and also we wanted to know if the lower back is in any way conflicted with the muscle activity due to the fact that we are carrying a backpack-like structure with the exoskeleton. We were also looking at the erector spinae. To make any comparisons of the EMG data between subjects, it is very important that we have a specific normalization of the EMG data. Otherwise, we couldn't compare the data of muscle activity between test subjects. So one of the most used ways of normalizing the data is the use of MVC, or a maximum voluntary contraction, in which the test subjects use as much force as they can prior to the real analysis, and we record the data on the maximum trials, and we use that to normalize the data in percent of the maximum voluntary contraction afterwards in the work scenarios that they are conducting. So when it comes to the data analysis itself, we use the Vicon Nexus software. I'm not going too much into detail, but I'm just listing it because you will see some screenshots of and some videos about how the recording will look like. So we had Vicon Nexus as a recording software where all the information was bundled into. So just one recording software for kinematics and EMG data. We use ProEMG to filter EMG data, smooth that, do the MVC normalization, we'll come back to that later, and to export the data afterwards in MATLAB. And in MATLAB, we conducted the calculation of joint angles with our own script, and I will also come back to that later. So we did also the deletion of outlier cycles and interpolation tasks and anything else. So statistics that I will go into detail in this presentation have also been conducted in MATLAB, and as you can see here, we've been using a statistical parametric mapping, and I will also come back to the intricacies of SPM, or statistical parametric mapping, in a short while. So if you look at data analysis of repetitive motion in this study that we conducted, in most cases it's pretty similar. First of all, you have the data acquisition phase, then you have the data preparation phase, and afterwards the statistical analysis of the data. So in our case, we used Vicon to do the data acquisition. So the synchronization of the different apparatus that we use, like EMG or kinematics, or you can also have force plates and other kind of data. All these data have to be synchronized in a way. So this is a huge problem when it comes to conducting research with a various amount of different tools. So you have to be very sure that the synchronization is up to the point, that all the problems that might occur, that you have different, for example, different frequencies in your apparatus that you will use. You have to make sure that these are synced up. Data preparation in our case with Vicon, I will show you in the next slide how we did that. For example, it was for the event detection, so that we actually can use the data after we filter that, so that we end up with the sequence of the data. I showed you that in the slide before. So the upwards and downwards motion of the data, and the cycles themselves have to be separated. And as you can see here, we used Vicon for data filtering, and there's another branch. So as after we filtered the data, the kinematic data was being used in Vicon, and that was the upper branch, and EMG data was afterwards used in ProEMG. After that, we did the data normalization and went to MATLAB, where we had an outlier detection. So we were looking at cycles that weren't a good fit for our research, because something occurred out of the norm of the cycles. And then afterwards, we have a statistical analysis of the data. So in MATLAB, so we have certain data extraction points. So that we are looking at from a statistical point of view. And in order to do that, sometimes the data has to be transformed in order to conduct your statistics, and you have then the possibilities of using, for example, a classic statistical analysis tool like SPSS, or have your statistical analysis being conducted in MATLAB, what is exactly what I will show you afterwards. So this is a short example of how the data acquisition looked like. So we had our test subject. This is an older, just an older movie I used to of the pre-tests, but it applies exactly the same way. It looks exactly the same. So we have the exoskeleton, we have a riveting task, and on the left-hand side, you see the actual video picture of the recording. On the left-hand side, on the lower side, you will see the kinematic structure. We have here full body model, but in our research, we just prioritized on the upper model. So out of this model, the shoulder angles are taken out and analyzed. Especially on the right-hand side, you see, for example, the force being applied on the force plate that we use. I'm not going into that in this presentation. Or as you can see here, the EMG of the shoulder, of the right shoulder of the test subject. So you see that every time the right shoulder is being used heavily, the EMG data goes up. In order to make sure that we have the cyclic data being analyzed properly, we need to do the event detection. So in this case, this is another program that we use, but you see that on the lower side that there are several event markers being placed, and the event markers that are used here are detected based on the fact that the test subject will place the rivet into the riveting pistol. So when both hands are close to each other, then an event marker is recorded, and we will use the event marker to cut the data into the specific cycles, and we end up with cycles that we can overlay over each other and have analysis on this cyclic motion. So everything afterwards is based on the event markers, so you have to make sure that the event markers are placed properly, because otherwise you will alter your data and your statistic will become false. So I'm using a few videos we did prior, because unfortunately I can't use the real MATLAB data at this point due to licensing issues. So this is the Nexus interface. You have your recording scenario, and everything that will be recorded will be happen inside that box. But I want to show you especially is something else. So a little break. I had to change the view of my presentation in order to skip through the video and show you what I'd like to show you. So we have the Nexus to Pro EMG normalization phase. Now we have conducted the data acquisition in Nexus, so all our data is ready to be used. And if we want to use the EMG data, I need to normalize that. So I will show you what we did in Pro EMG in this case. So the data will be transferred to the EMG software, where we have a look at, for example, what happens in the MVC tests. So the maximum voluntary contraction test we did, for example, 3 times the maximum that you can achieve in each of the muscle prior to the test that we will conduct. We have the data. We also have to separate the data, and then we will have an overlay of these EMG data of the EMG MVC tests. So after we did that, we have to do the normalization, and we will see that the normalization will give us a certain point of maximum muscle activity in these 3 tests that we did prior to the working sequence, and we will use these top activity as the base of 100% of maximum voluntary contraction activity that we can see with this test subject, and all the rest of the activities that will happen afterwards in the working sequence will be based and normalized on these tests that we did prior, so that, for example, during the working activity, we will have an activity that is not 100% of the maximum possible activity of the shoulder of this test subject at this specific day, but maybe it will be around the 20 or 30 or 40%, and we will use this as a reference frame in order to make sure that we can afterwards compare the data between subjects based on their own maximum activity that will occur in these test phases prior to the real working activity. So all of these will be normalized, and then we will find the point where we have the maximum, and this maximum, this will be the reference point, and we will conduct the analysis further with this reference point in mind. So next up in the data preparation phase, and before we can do the statistical analysis of the data, we have to make sure that we will only put into the statistical analysis what we think is a real picture of a reality. And for that, we have to make sure that any outliers that occur, so any cycles that do not fully represent the other cycles, will be eliminated. And to do that, we use the events and markers that we used prior. And now you see an example of an outlier detection elimination process that we did. So, for example, this is an angle that occurred with the shoulder. So you have a certain shoulder angle, and you have 15 different cycles, time normalized and being placed on each other. This is what you can see in this picture. So the thick blue line is the average shoulder angle that you can see here as a representative of all the other angles that are displayed over here. But as you can see down there, the 2 gray lines down there, so these are the outliers of this particular instant. And so what we did is that we I'm going to show you that. So we identified the outliers for every single person, and so we had, for example, 15 cycles recorded, and the 2 cycles that differed the most out from the average, these were picked and afterwards deleted, so that we have an outlier detection. The criteria for the outlier detection is solely based on the research you're doing. So you have to decide what is an outlier, so what qualifies an outlier. There's no real answer in what qualifies an outlier other than the thought process that goes into your research, and you have to be able to really tell, okay, I'm going to do the outlier detection based on certain criteria that I'm open to discuss and that I'm willing to defend. And in my opinion, it is very good to have a real prior look into what determines an outlier and why you want to do that. Sometimes it's not necessary to do that. If you have, for example, cyclic data, let's see, for example, on a bicycle, and it's very, very similar each time. But if you have any kind of repetitive motions where, like in our case, we have not confined space and the trajectories are relatively freely available in the 3D space, then it's a good idea to look for outliers. Otherwise, your data will be of lesser value afterwards for the statistical analysis. Here I can show you what is the point in the deletion of the outliers when it comes to the outlier cycles. We have here, for example, the data in Pro EMG. So this is the EMG data, and these points down here are the event markers that I showed you prior. And so we have all these cyclic motions and the EMG data inside the cycles, and you can see here that we have also, based on the different muscle activities, all these cycles that we recorded. So in our case, we use the kinematic data and the outliers of the kinematic data to identify cycles that we would take out and delete, also of course from the EMG data. For example, if the first cycle alters in the kinematic drastically from the others and is considered to be an outlier, we have to also, of course, delete that cycle prior to the statistical analysis, so that only the same cycles that go into the statistical analysis from the kinematic data will also be in the statistical analysis of the EMG data, so that there is no difference between the analysis of EMG and kinematic data. In order to make sure that we delete the outliers in MATLAB for EMG and the kinematic data, we used MATLAB to open all the data points and to eliminate the different outlier cycles. So what you see here is that we are using MATLAB and read the data from the Vicon, where we have the kinematic and the EMG data stored. So the format that Vicon uses and a lot of kinematic software is using is C3D, and C3D can be considered a container format in which you can have a lot of biomechanical data stored. There is a free software available, free extension for MATLAB, which is called the Biomechanical Toolkit, that I could really, that I think everyone can benefit from, because with the Biomechanical Toolkit, you can actually use that in MATLAB to read C3 data and have basic analysis being conducted, as well as using our own scripts on top of that. And you will see here that we have several of these data points analyzed or copied, in which I will show you, and we are using that so that we can create these different cycle overlays on top of each other for every single muscle and every single joint in the same way. So whereas the preparation of the data will separate between the kinematic data and the EMG data between Vicon and in our case Pro-EMG or the EMG data, the software of your choice. In the end, everything will come back to MATLAB in our case, and we don't care so much if it's EMG data or kinematic data. In the end, we want to have cyclic data overlays in the same fashion from the kinematic as well as the EMG data. And this is then how it looks like in the end, all outliers deleted, so that we only have the cycles that we want to put into the statistical analysis in the end. So here in a little bit bigger picture, you can see that we have, for example, all EMG data stored in MATLAB as an overlay of all these different cycles and in percentage of the maximum voluntary contraction for the muscles that we've been looking at. So shoulder muscles on both sides, and in our case the lower back muscle on the dominant side of the human body. And the kinematic data itself will look exactly the same like this. So overlays of cyclic motions, time normalized and on top of each other, so that we can create, for example, an average line of the muscle activity or the kinematic data, so the joint angles. So what we end up with are continuous data of the cyclic motion separated by the specific endpoints of the motion, and we have repetitive motion overlaid on top of each other. And this will lead to the statistical analysis that I will show you right now via SPM, so statistical parametric mapping. So this is an exemplary data. Out of this study, we have a cycle, we have in this case a kinematic angle, so you have the average and the standard deviation of these motions of the cyclic repetitive movement. So here I'd like to come back to the problem I have talked about in the beginning. So where are the knowledge gaps? So in former years, it was that we used these angular motion to look at specific points in time, for example, the minima or the maxima of the motion. So for example, if we're looking at the maxima of the angle, the specific angle we're looking here, we would say, okay, there is a difference in baseline, which will be the red one, and the intervention, which will be the blue one. And we say, okay, there's a difference at that point in time and in comparison to this point in time. So where is the maximum? So you see where the problem lies in that kind of analysis. And this angle motion, for example, it could be that or you can see clearly that the peak motion, peak angle occurs over here with the baseline, but the peak in the intervention is over here. So if I compare the peak angle, I compare totally different points in time. So this can drastically changes the outcome of the study when I do not have a reference frame regarding the time component or the continuous component of the data that I'm analyzing. So what I want to do is I want to look, regardless of a specific point in time, I want to know where these both angular or the angles of this joints will differ statistically significantly from each other. could be over here, but it could also be in the middle of this part. So do we have statistical differences over here? Do we have statistical difference over here? This is what I want to know. And statistical parametric mapping allows us to do so. So the origins are in EEG analysis, and every one of you who's doing an EEG analysis already know statistical parametric mapping, and it has been adapted for biomechanical data analysis of continuous cyclic data by the group from Pataki et al. In the recent years. So going back in my other mode of presentation, I can show you what occurs with the SPM data in the analysis we conducted over here. So what do we want to know? We want to know alter these or differ the baseline and the intervention from each other at every single point in time, regardless of the outcome, so regardless of the amplitude. So SPM conducts a statistical analysis for each percentage point of that cycle, and the result is a trajectory which is called the one-dimensional T trajectory. So this is the statistical outcome of that analysis. In this case, we calculated the T threshold based upon random field theory for a two-sided t-test. So we conducted two-sided t-test for every percentage point in that in this case. So this leads to threshold values above and below, and every data point that is outside of this threshold is a statistical significant difference. It would be too much to ask to go into the fine details of SPM analysis and how that can be done with SPM analysis, and what are the basis in statistics and mathematics in order to do so. But all I want to say here right now is that this statistic is based upon the characteristics of the data that you recorded. So it's not something that you're looking at a table, for example, like with normal statistics, where you have certain areas in which you will see, okay, this is considered to be a significant difference. It is based solely upon the characteristics of your data, and you have to do the analysis always based on your data. So every time, as I mentioned, we go outside with our threshold outside of or with our T trajectory outside of the threshold, we have a significant difference. And the significant difference for numerous data points that are next to each other, we call that a supra-threshold cluster. So in this example, from, let's say, 4 to 5% of the cycle unto 27% of the cycle, let's say, we have a significant difference in data. Which means, coming back to our kinematic angle, or the joint angle that we see here in this picture, we have a significant difference in this part of the cycle. Based on the data, we do not have, for example, a significant difference in here. Although it looks pretty different, the mathematics, statistics will not support that conclusion. So how does the analysis will look like with SPM? So to go by step would take too long. So therefore you will have to use SPM analysis workshops, where you will go into the details how you will do that. I will show you, based on the video, just how this will be conducted in MATLAB in general, so that you will have a broad or a rough idea how that occurs. And then if you are interested to do so, SPM delivers a lot of information on the net about how to conduct these experiments by yourself. So SPM for biomechanical analysis that is provided by the group around Pataki, they give you a MATLAB extension as well as an extension for Python, so you can use it both ways. I will show you the MATLAB version in here. So what you can see here, we have MATLAB, we have our data ready at hand at the in the let's say the cycles that we used that I showed you before. The data is at hand, let's say in CSV, so comma separated value format, and then we can conduct our experiments with SPM. So we have this extension SPM in MATLAB. We only need to read the data, and if we do that, the data will look similar like this. So for each angle or for each muscle or that you want to analyze, you will have one CSV matrix which has to be formatted in a certain way. In most cases, when you're working with data, you have, for example, CSV data, and then you have one value, and over time you have the differences going down in the column. Whereas in SPM, you have to transform the data so that the data will be not in the columns organized, but in the rows. So for example, the data will look like this. We have, this would be the equivalent of, let's say, 20 cycles. And for each cycle, you have the data point 1, 2, 3, 4, 5, and 101 data points to have the cycle for 100% represented. When this goes into the SPM analysis, there are certain ways you can analyze your data. So what you can see here is still the transformation of the data, but then, for example, what we need to do is we need to do normalization tests, and we also want to show the data as well. So this, for example, this is the data distribution. We have a baseline, we have an intervention, and we have the standard deviation, and you can do that in MATLAB, in SPM, and show that. Then you have the normal test that you do. You have tests for normal distribution. So using all the known ways of analyzing the data, you can have so tests for normal distribution, you can have tests for ANOVA, t-tests, regression analysis, all the things that you are used to doing SPSS, for example. Most of them, or most cases, you will also have the equivalent in SPM available for the continuous data. And if you want to know more about how this can be applied, I refer you to the spm1d.org website, where it is shown how to really use that data and how to use the different types of analysis. I want to just show you that all this analysis is being conducted here in MATLAB, and we end up with t-trajectories, for example, for normal distribution tests, and we end up with, as you can see here, different tests, for example, two-tailed t-tests with the data, and then you end up in the end with these informations that will tell you, are there any differences, are there any suprathreshold clusters, are there significant difference in the data or not. And also with SPM 1D, you can then afterwards plot the data, and you will end up with these plots, for example, where you have the cycle, you have, as I mentioned, the thresholds, and you see where the data will actually differ from each other. Having talked so much about how we go forward in analyzing the data, I'd like to show you the results of the study we conducted, show you how the SPM analysis results will look like, and what is now different to, let's say, normal analysis that you will have with using discrete analysis with discrete points. So looking at the working sequence riveting right now, on the right-hand side, you see the statistical analysis with SPM displayed right on top of the data itself. So by that time, you already can see, okay, where are gray underlined areas? And you already know now, okay, there's significant difference. And how does that look like in our case? So if you recall, we have the upward motion, so hands are in front of the body, so the rivet is placed into the pistol. We have the T2 point in time where the pistol is on top, and we put the rivet into the ceiling, and we have the downward motion. So because the exoskeleton is actually producing a force that is applied onto the shoulder, we have to know what kind of torque distribution is being applied. So when does the exoskeleton actually supports us with force? And what's being used in riveting was torque distribution. This is the blue line, and I'm going to explain that. So at 30 degrees of shoulder flexion, when the arm is lifted, there's no support in the beginning. So the arm is dangling, the arm is low, nothing happens. Then the arm is going to be flexed, hand goes up, and with 30 degrees of flexion angle, the exoskeleton actually distributes a torque, and it reaches its peak at around 80 to 90 degrees of shoulder flexion angle. So when the arm is outstretched in front, then we have the biggest torque distribution. When the arm goes higher up, then the distribution of the torque lowers, and around 145 degrees, then no torque is applied on the human body whatsoever again. Looking at the shoulder flexion angle that happens during the riveting task, we see that in the beginning, the arm is low, the arms are raised, and we have a shoulder flexion of approximately 100 degrees, around 100 degrees in the top, and will go down again when the hands meet in front of the body. So for abduction, we have a slightly different angle motion, but you see still the case that we have a combining abduction angle in the case that the arms are dangling down, so the arm is always a little bit abducted in the beginning, and when we go up, the abduction angle also goes up in the middle. Where the flexion is the highest, the abduction angle goes down, and then because we have a cyclic motion, we have this mirror-like phases where the angles in the first half of the motion are quite similar, or the exact opposite of what happens in the second part of the motion. So, but what SPM can show us is where exactly do we have significant differences? In which part do the exoskeleton alter our motions? And we see that here shoulder flexion we have significant increase in shoulder flexion for that time. So the exoskeleton is pushing the arm a little bit higher than without the exoskeleton. And we see a little bit lower angles here in the flexion at the dangling down of the arms. Looking at the EMG data, we see that when we look at also these places where the exoskeleton actually does something, so this is the area between 30 degrees going upwards, going downwards. So there's the actuation going on, and we're looking at what happens with the actuation and the muscle activity, because this is the interaction part we're interested in mostly with the exoskeleton. When we look at that, we also, oh no, so sorry. So there's some points about the shoulder flexion, so the data points I explained prior. We'll go over that, and we'll come to the muscle activity. There we are. So with SPM analysis, with the muscle activity in the same realm, we see also that we have this actuated area above 30%. We know that because the sequence, so where it starts, derived from kinematics, and this is identical, so it's the identical dimension. So what we see in kinematics, we see if in kinematics the actuation occurs here at around 18% of the cycle, we know that also actuation occurs at 18% of the cycle for the EMG data, because it's the same time frame. Looking at that, you see that for the deltoid dius anterior, for the shoulder muscle in front, as soon as we have actuation of the exoskeleton, we have a significant difference in needed muscle activity for the same task. So baseline is the red one, Lucy exoskeleton is the blue one, and we see as soon as we have actuation of the exoskeleton, the shoulder muscle in front really significantly works less, and this goes throughout the whole actuated time area and time space. So this is a major outcome of this study. Interestingly, the trapezius, the muscle above the shoulder to the neck, does not have any significant difference. So no difference for the trapezius. And when we look at the lower back, for example, we have no significant difference that occurs, but at the end of the cycle. And we were, for example, thinking about how that occurs. And the outcome was that when we lower the arm, we have to work against the resistance of the exoskeleton, because the exoskeleton pushes the arm up, and in this case the exoskeleton does the support on the way up as well as on the way down. Here it's a relief. Here it is there is some additional muscle activity needed in the back to stiffen the back, to press against the exoskeleton, and this is the outcome of the increase in muscle activity at the lower back you will see at the end of the motion. So, in a short overview of the study results, we saw that the muscle activity reduced significantly in the riveting task above head level to a great extent. The difference between traditional biomechanical analysis with maximum and minimum or averages is that we can see where the changes actually happen during the motion. So the analysis of the repetitive motion is quite different to traditional statistical analysis when I'm able to look at the whole motion in all its complexity over time. So using continuous data and analyzing continuous data as such, not as discrete points, but as a continuous data, allows us to not make any assumptions prior to the study where we might find differences, but take a step back. Do not make any decisions prior on what we're looking at, but just look at the data, the continuous data, and see where significant changes occur in kinematics or in EMG, or could be also any other type of continuous data. So in general, we saw that the exoskeleton Lucy showed great potential in reducing musculoskeletal ailments due to overload of the shoulder, but also we saw a lot of areas for improvement. I was not going into detail in this presentation because that was not the part, but I just wanted to show you that we saw, okay, we had differences in shoulder angle. We wanted to reduce that, so the shoulder kinematics have to be changed. The back structure, I showed you a little bit about the increase in muscular activity at the back. We needed to change things in that. Also, test subjects reported on problems with the interfaces. They felt sometimes quite uncomfortable, and we saw that because we have the different torque distributions applied with the exoskeleton, that we needed more work in order to make sure that the force application really fits the needs of the different working activities, because we did not only test it for the riveting task that I showed you in this presentation, but for grinding tasks and a bunch of other tasks as well that will happen and occur in the workspace. So what is the goal of this research study? After numerous research cycles, iterative developments that all happened, I showed you right now. So we had the exoskeleton Lucy 2.0. The study was conducted in 2018, and then we had a lot of iterative cycles, and ended up with the company that really produced now this type of exoskeleton S700. And you see there are quite some similarities between the prior study of the exoskeleton Lucy 2.0 and now what we're coming out with during this year with the S700. You see there are similarities, but there's also, regarding, I told you about the shoulder kinematics, there have been there was a lot of improvement on that, and so this is something that can so the improvements can be derived out of these biomechanic analysis, and especially the analysis of the continuous data helped us to a great extent to see where problems occur that we didn't expect prior to the analysis, and we could really see the benefits of the engineering development in regards to the changes in the altered angular outcomes. So in this case, I'm very happy about what we achieved, and I hope that I was able to show you a little bit about how we conducted our experiments, and it gave you a little bit of an insight of how you might go forward with your own studies, and I hope that you will have a great workshop, and I thank you very much for your attention.